Let's look at an example where we have to find points of inflection and the intervals where a given function is concave up and or concave down. So find the points of inflection and the intervals on which f of x equal to which is the function 3x to the fifth minus 5x to the fourth plus 1 is concave up and concave down and concave down, concave down. So we need to compute derivatives here. I mean, everything here has to do, with the theorem, the test that we just presented before. This test for inflection points, which tells us that if f double prime is either 0 at a point or if it doesn't exist, and if you have a change in the sign of f double prime, then f has to be an inflection point at that point. It has to be an inflection point. C has to be an inflection point. So we need to compute derivatives. So what is the f prime of x? Is 15x to the fourth minus the 20, minus 420 x to the third, well, plus 0. F double prime, which is where all the information in concavity is encoded. Remember, we cannot draw any information about concavity from f prime or from f, just from f double prime, at a point. Because, if you know that f prime is increasing, you know that the function is concave up. But knowing the sign of f prime doesn't tell you anything about the concavity of the function. Okay, so f double prime of x is then 60x cubed minus 60x squared, which factors as 60 times x squared times x minus 1. And again, then f double prime of x is going to be equal to 0. Then you're going to have candidates for inflection points. The points x equals 0 and x equals 1. Okay, so what are the intervals here? The intervals here are minus infinity to 0. We have only two candidates here, so we split the real line into three intervals: minus infinity to 0, then from 0 to 1, which is the next candidate that we have for an inflection point, and then from 1 to infinity. That's the interval. Remember to know the sign of the second derivative, just like in the case of the first derivative test, to know the sign of the derivative, of the second derivative, we simply need to test at one point inside the interval because the sign remains unchanged. So this is the sign, and we're going to record that into the third column, sign of f double prime, and then we're going to have we're going to write down what is the behavior, meaning whether the function is concave up or down. So here we're going to use some test value inside the corresponding interval. Okay, so in between minus infinity and 0, so we cannot pick 0 because that's where f double prime is 0. So we need to pick anything smaller than 0. We pick minus 1, and f double prime of minus 1 is minus 120. You can check it by plugging this in here. So x is -1, so you get -2 from this, and here you get 1. -2 times 60 is -120. So the sign of f is negative, right? So it's less than 0. Between 0 and 1, we can pick 1/2. And so that is, I mean, if you do the arithmetic, that's going to give you -15/2. Okay, so you're just going to get -15. Just we're going to get -1/2 from this factor here. And you're going to get 1/4 here, so -1/8. And 60 is 4 times 15. So you can cancel out the 4 there, and you get -15/2. So again, the sign of f is of f double prime is negative. And now f double prime of 2. 2 is a point inside this interval. 2 is greater than 1. Okay, so then the double prime of 2 is 240. 240. This term here, the x -1, this gives you 1. This gives you 4. 4 times 60 is just 240. And the sign of f double prime then is positive. And the behavior of f is, well, the sign of f double prime is negative. It means that the function is concave down. So concave down. Again, between 0 and 1, it's concave down, right? And after 1, the function becomes concave up. Concave up, and this is enough to conclude and to classify the and to give the inflection points of this function. So there are only two candidates, x equals 0 and x equals 1. But we'll see here that at 0, the sign of f double prime did not change. So it was negative before 0, and it's still negative after 0. So the function, the function doesn't change concavity at 0. So it's not. 0 does not correspond to an inflection point. This is another case for 1. At 1, f double prime is equal to 0, and the sign of f double prime between 0 and 1 is negative, and after 1 is positive, so it's a change in concavity, as you can see in here. So there's a change in concavity. The function was concave down, then became concave up after 1. So f double prime equal to 0, and there's a change in concavity. Then f has a point of inflection at 1. Okay, so the conclusion here, f double prime does not change sign at 0, right? At x equals 0, doesn't change sign, and so this implies that 0 is not an inflection point, because it doesn't satisfy one of the required properties. It's not an inflection point. It's not a point of inflection. F double prime, so this is the first thing, f double prime changes sign at 1, and this implies that 1 is indeed an inflection point. It's an inflection point. Okay, just before moving on, remember as a note that a point of inflection does not need to correspond to a point where f double prime is equal to 0 necessarily. An inflection point can also occur at a point where the second derivative does not exist, or is not defined. So okay, so we're gonna conclude the video with a theorem that, based on the concavity of a function, we can tell immediately whether a critical point is a local min or a local max. This is something we anticipated before. So this is known as the second derivative test. This is the second derivative test. Remember, before we went over the first derivative test. So once we assume more knowledge on the second derivative, we can apply this test over here. We have a point, a critical point, B, so let's C be a critical point of a function f. Then if f double prime exists at the point, so you can evaluate f double prime at the point, double prime to C exists, then we can say that if f double prime at the point, this is assuming the second derivative is continuous. Okay, so if double prime at the point is greater than 0, then f of C is a local min. F double prime, on the other hand, if double prime is less than 0, then f of C is a local max. And if f double prime at C is equal to 0, then the test, unfortunately, is inconclusive. What's going on is that f C may be local min or max or neither. A local min, local min, local max, or neither, or neither of the two. Neither. We actually explained how this works. The first 2 points work. So if f double prime is greater than 0, it means that the derivative, so f prime, is increasing. So if its derivative is 0 at the point, or it does not exist, it doesn't matter. The f, it does matter. For this particular test, in general, it doesn't matter. So because you have the first derivative test. But if the second derivative exists, f double prime being greater than 0 at a point means that f prime is increasing. So that means that if it passes through 0, it must have been negative before, and is increasing. Oh yeah, so it's increasing, so it must be negative before, and it's positive after the value. The value of x equals C. So it does something like this, right? So this is the situation. So it's a local min. If the second derivative is negative, then the function is concave down. So this is a local max. And if f double prime is equal to 0, we cannot really tell whether f is local min, max, or neither. And this is actually it suffices to look at the example of x cubed and x to the fourth. And x to the fourth, x equals 0 is a critical point, and the second derivative is 0, and that's a local min. X cubed, on the other hand, x equals 0 is it's a point of inflection. It's a critical point and it's a point of inflection, and we saw that example in the last video, and it corresponds to neither a local max or local min. We'll continue in the next video then.